taking up question number 5 on page 13 of the energy workbook, and this question will be found in the topic 6 homework. So question 5 says 500 grams of glycerin at 10 degrees Celsius is added to 1 kilograms of water at 1 degree Celsius. Calculate the final temperature of the mixture. So a good way to start this question is just by drawing a little diagram that just helps us better understand what the question is, what the question has given us, and what it's telling us to do. So we can say that this is the glycerin, and we know that it's 500 grams, and we know that it's at 10 degrees Celsius. And then here's the water. We know that the water is at 1.0 kilograms, and that it's at 1.0 degrees Celsius. And this is going to be glycerin plus the water, and what we're trying to find is the temperature of the mixture. So now that we've done the diagram, I'm going to be making a more formal list of our givens over here. So we can start by listing the mass of the glycerin, which the question says is 500 grams. Or you can also say that it's 0.500 kilograms. And the reason we want to do this is because all of our questions are done using kilograms, and if we do it in grams, we're not going to get the right answer. And then the question also tells us the initial temperature of the glycerin, so T1G, and that is 10 degrees Celsius. It also tells us the heat capacity. Actually, the heat capacity can be found on page 12 of the workbook, and these are all the heat capacities you need. But this is where I found all my heat capacity values from. So according to the table, it tells you that the heat capacity of glycerin is 2.4 times 10 to the 3 joules per kilogram degrees Celsius. Now, we can write down the mass of the water, which is 1.0 kilograms. It tells us the initial temperature of the water, which is T1W, 1.0 degrees Celsius. And then we need to know the heat capacity of water, which is 4.18 times 10 to the 3 joules per kilograms degrees Celsius. And again, that value is just taken from the table on the previous page. And now what we're really trying to solve for here is the initial temperature of the final temperature of the water, and then the final temperature of the glycerin. But if you really think about it, the final temperature of the water and the final temperature of the glycerin are going to be the same. So what we can say is let T2, which essentially just cancels out, it doesn't specify what substance is, just saying final temperature is equal to T2W, which equals to T2 glycerin. So this is going to be important for when we're solving the question later on. So that's all I want to do for my givens. And now we can start using our equation. So the equation that we're going to use to solve this question is the one that we used for the conservation of energy. So what we can say is that the change in thermal energy for the glycerin plus the change in thermal energy for the water is going to be equal to 0. And this stands true to the law of conservation of energy, which states that energy cannot be created nor destroyed. So essentially, the amount of energy lost by the glycerin is equal to the amount of energy gained by the water. And because one value would be negative, one would be positive, they equal 0. So now what we need to do is expand out both of these variables here. So we can say mass of the glycerin times heat capacity of glycerin times the change in temperature for the glycerin plus mass of the water times heat capacity of water times the change in temperature of the water is equal to 0. Again, this is the same thing, it's just this has been expanded out a little bit further. So now what we can do is expand out the change in temperature, and it'll look like this. So the mass of glycerin, heat capacity of glycerin, and now we're going to call it T2, so the final temperature of glycerin, minus the initial temperature of the glycerin plus mass of water, heat capacity of water, and the T2 water minus T1 water equals 0. So now, because of what we stated over here, we can essentially cancel out these two here, and now it just becomes T2, and it's not specified T2 glycerin or T2 water. And this makes sense because when both the glycerin and water are mixed, they're going to be at the same temperature. So there's no reason to really have this specification here. So first we'll cancel out this letter here. And also what we can do now is distribute. So we can distribute this into here, and then this into here, and then we'll distribute this into here, and this into here. So what it's going to end up looking like is mass of glycerin, heat capacity of glycerin, and then T2, so not T2G, just T2, minus the mass of glycerin, heat capacity of glycerin, T1 glycerin. This letter still stays because the initial temperature of the glycerin and the initial temperature of the water are different, so we have to leave the G here. And then we have the mass of the water, the heat capacity of the water, and T2, so not the W anymore, minus the mass of the water, heat capacity of the water, T1 water equals 0. So all we've done up to this point is really just expand it out. So now what we want to do is, since what we're trying to solve for in this question is really T2, because we're trying to find the final temperature, this is what we're trying to solve for, what we really want to do is try to make both the T2s on one side, and these two that don't have T2, we want to move them to the other side. So we're going to move this and this over to the right side. And now it's going to become this. So mass of glycerin, heat capacity of glycerin, T2 plus, because this is positive, mass of water, heat capacity of water, and then T2. And then we say equals, because now we move these over, mass of glycerin times heat capacity of glycerin, T1 G plus MWCW T1W. And then both of these became positive because they're both negative here. When you move them over, they become positive. So now what we can do is we can factor out these two T2s. So what it's going to look like is T2 and then MGCG plus M water, heat capacity of water, equals MGCG T1G plus MWCW T1W. So I didn't change anything over on this side. This side stayed the same. All I did in this step was factor out the T2. So now, since we're trying to isolate T2, that's our main goal here, we can divide both sides by what's in the bracket here, and we'll divide this by, this will be divided by this. So what it's going to look like is the mass of glycerin, Cg T1G, plus the mass of the water, C1 T1W, and then divided by whatever was on this side, because we divide both sides by this, and then on this side, whatever's in the bracket cancels out, and then we're left with T2 on its own. So MgCg plus MwCw. So there is all the algebra that you needed to do to isolate for T2, and now it's just a matter of subbing in our values from all of our givens up here. So start subbing in. So the mass of the glycerin, which we said is 0.500 kilograms, times the heat capacity of the glycerin, which is 2.4 times 10 to the 3 joules per kilogram degrees Celsius, and then times the initial temperature of the glycerin, which is 10 degrees Celsius. So it's going to be this plus the mass of the water, 1.0 kilograms, times the heat capacity of water, 4.18 times 10 to the 3 joules per kilogram degrees Celsius, and then times the initial temperature of the water, which is 1.0 degrees Celsius. So all of this, and then close bracket, all of this divided by the mass of the water, mass of the glycerin, glycerin times the heat capacity of the glycerin, which is 2.4 times 10 to the 3 joules per kilogram degrees Celsius, and then plus the mass of the water, 1.0 kg, times the heat capacity of water, 4.18 times 10 to the 3 joules per kilogram degrees Celsius. So, subbing, once you put all of this into your calculator, I've already calculated this value before starting the question, so you should get approximately 3.00743 degrees Celsius. But if we go back to the question here, we can see that the lowest number of significant figures is 2. So we can say that our final answer, that the final temperature of the mixture is approximately 3.0 degrees Celsius, rounded to 2 significant figures. So now we can make our therefore statement and say, therefore, the final temperature of the mixture is 3.0 degrees Celsius. And there is your final answer. And if we go back to the workbook here, it's the exact same. So there is the solution to how you solve question 5 on page 13 of the energy workbook. And most of it is essentially just figuring out the algebra and isolating for T2 and then just subbing in your values.